Okay. Now we have 1 over b minus a, and then all the f plus plus plus, and then delta x. The f x1 until xn, we can write the sigma. Okay, we can write in the terms of sigma. So this will be sigma from 1 to n. Let's just write this sample point, and yeah, just write this as our expression. And then we can approach with limit, making the n going infinity. And then we can write this as so this is the average value. And from this average value, we also have mean value. Okay, from this average value. Okay, it's one package. I will show you later in the next slide. Okay, so the idea is just put 1 over b minus a in the front of the integrations. Okay, and a and b is the endpoint of the integrals. Okay, so we call this the average value of our integrals. Okay. Okay, let me go to the next slide. And let me write the mean value. The mean value theorem in integral. So if the function is continuous on, let's say AB, we keep the same expressions, then axis C, okay, in AB. So it's similar to the derivative, okay, but we are using the integration. So the C, or the function of C, is the average value so we can write that the integrations of the functions is okay. So I think it's not too complicated. It's actually easy to understand. So you have a set of numbers from A to B, okay, and you know that the average is 1 over b minus a integration. Okay, you know the average, like you have average of the score in the class, right? The average means usually in the middle ground, right? So in between A and B. So we can say that based on this theorem, there will be a C, okay, that is actually the same value as the average value. Okay, so we can conclude that the integrations from a to b of the functions is f of that number, the c, and b minus a. Okay. And that is for chapter 6. Okay, and done chapter 6, and we move to chapter 7. Okay. So let me write chapter 6 and okay. So chapter 6 is from the area, right, between curves, volume, and this average and mean value. Okay. Okay, let's move to chapter 7. So chapter 7, I will start with the integration by part. Okay, let's consider f is okay. Consider this. If it is the product rule, then we can write this as f prime g plus g prime f. And let me write f g continuous and differentiable. Okay, we can write more functions like this. And let me write the big F. Let me write in terms of fg. Okay. And the f prime, let me write in terms of d dxs. Okay. It's the same thing. Okay. And plus the d dxg. Okay. Let me make a little bit. Okay. Now, from these expressions in the product rule, let's take an integral. Okay. Take the integral. The whole thing here, the FG integrations, it perfectly becomes FG. Okay. And this becomes G. Let's write the F prime. When you integrate, it's become df in the side, okay? Like dx. And this become f dg. Okay. And let me rearrange the structure. And you get now f. You can write like fg, gf. It's still the same. It's still the same. But the general equations is integration fdg, fg, gdf. Or maybe you are familiar with the u, right? Let me write if u is f of x, and then phi is g of x. Okay, so du will be fx dx, and d phi becomes gx dx. So I can write this as the complete version f of x. dg means the g prime, that I can write the g prime x dx. Okay. Equal fx dx minus integrations gx and then f prime x dx. So let's change to u. So integrations of u d phi perhaps this is the expression that maybe most of you familiar with. Okay? So how we can come with these conclusions? Okay, maybe in your high school you just use the operation and you just calculating, but actually it's from the product rule. You arrange the product rule and integrate the product rule, and you get this expression. Okay, so whenever you have like integral x sine x dx. So we can separate the x sine x and choose which x is u. Okay. So for example, I want to make u is x and d phi is sine x dx. So we need to find du and we need to find phi, and we put into our equations here, and we can calculate easily. Okay. For example, this integral of x sine x. Okay. Let's write the u is x. So our du is dx. And write the d phi is sine x. So phi is negative cos x, right? And then we need to set up the equations. So u phi and then minus phi du, or become plus because of negative cos. And this is become plus a little bit range any functions that you can separate become two functions. Okay, so most of that functions can be evaluated with the integration by parts. Okay, and you can write become this and plus c. Okay, so you need to choose u and d phi wisely. Okay, sometimes it works if you switch. Sometimes it doesn't work. Okay? So you need to keep that in mind. Okay. And maybe because it's always having the integration at the end, maybe when you solve the integration here, you need to use another method. It may be for another case. Okay, but I think for this case, the simple one is directly giving the cos x, and we can integrate easily. Okay. Okay, let me give you some examples and then conclusions how to simplify this method. Okay. Okay. Let's try the simple one first. Okay. Let's try the ln. Okay. This case, of course, it's only having ln x and then dx. Of course, the only possible for dv is dx, okay, because it's easy to integrate, and the u is ln x. If we switch them, it's impossible to be written because you don't really know the integration of ln, right? But you know to derive ln, right? That's to keep in mind. Okay, ln you cannot integrate, but you can derive, right? Okay. So let du is ln x. So you get du is 1 over x dx. And dv is the x. And v is x. So let me write here. Ln x dx is x ln x minus, so it's canceling, and we get the results is ln x. It's 1, so it's become only x, and then plus c. Okay. Okay. Let me give you another one. E to the x sine x dx. Can you try this one? E to the x and then sine x dx. I believe if you switch u and dv, like maybe u is e to the x and dv is sine x dx, you want to switch maybe u is sine x and dv is e to the x and dx, it may it may it might be possible. You can switch and the results will be similar. Because e to the x, you differentiate, you integrate, still same, right? It's e to the x. But sine x, it, derive, integrate, it become cosine or negative cosine, right? So maybe you will see some repetitions. So let me try the u is e to the x. So du is e to the x dx. And dv is sine x dx. So v is negative cos x. So let me write this. So it becomes negative e to the x cosine x, negative, and let me write this positive. Okay. Now we get another part here. We may do the same thing like we did before. maybe it is u and d phi. Let's just try one more. And it's become sine x when you integrate cosine. So let me write the complete e to the x sine x dx. So write the u phi is e to the x sine x minus the sine x e to the x. Okay. If you write the equations in complete equations, if you write that, maybe you are focusing on the right hand. You get this, you try one more time, right? U dp, u dp. It will completely, you will repeat all the integration by parts. You did this, get this, and you did like all equations, right? Repetition. What you need to do is, you see here, e to the x sine x. Move this to the front, okay? Move this to the left. And you get 2, right? And what you need to do is just divide by 2. And that will be the answer, okay? That's also something that can be happen in integration by parts. If you see functions that when you derive or integrate, it becomes the same, or it have like, maybe it's e, maybe it's e x squared or e to the 2x, but at least if you derive, it will never be 0, right? At least it will have the e. If you see that, you need to write the complete equation to see the form, okay? Like this one. Then we can move this to the left, and it's become 2. And let me write this as e to the x, and then sine x minus cos x. And then divide by 2. And I will add the constant at the very end, okay? Because if you add here, it might confuse you. So just add at the very end, the constant. Okay? So especially at the exponential, the e, this will be happening a lot. Okay? So you have another functions that is actually our original function at the beginning. So you need just to move out the functions and divide all by 2. Okay, any questions? Get it? Okay. Okay. Okay, I give you one another example. X to the 4 ln x dx. See if you can find the solution. And I hope at the very end, I can give you some idea to help you rearrange the structure. So you need to pick u and d phi. But remember, I've told you before, we have ln here. If you take this as d phi, you will be lost. You are not going anywhere. Okay? So ln x, choose that to be derived. Okay. Okay. Now we need to choose the u is ln x, because if you choose d phi, then we cannot go further. And du is 1 over x, and d is x for dx. So phi is, so we can set up the u phi is minus integral of x to the 4 dx. Plus c, or maybe we need to write down the yeah. Okay, I think that's uh, not too complicated. Okay, let's try the other one. X squared sine 3x. Let me write in the new page. Okay, another thing to choose the u and d phi. You see, we have x squared and we have sine, right? Sine function. Sine functions, you differentiate, it's never zero, right? Sine, cos, sine, cos, repeat all over again. One thing to keep in mind, if you see that repeatable functions do not make the s derivative. Make the u x squared, because x squared you can derive until zero, right? So if you have zero, then you can stop, right? So this is u and d phi. It's much more easier. So let's choose x squared as u. So we have du is 2x dx, and d phi is sine x, sine 3x dx. So I get phi is negative cos 3x divided by 3. Okay, let's write the integration by part. And then minus, or rather it's become plus 2x cos 3x over 3 dx. Oh, let me put the 1 over 3 outside. Okay. Now we have 2x and cos 3x, right? We do the same thing as before. So this become u and d phi. Okay. So u 2x. So du is 2 dx. D phi is cos 3x. And phi will be sine 3x over 3. Let me concentrate on this part. So u phi is 2x sine 3x over 3 minus 2 over 3 sine 3x dx. And this whole thing should be multiplied by 1 over 3. Okay. Let me move this to outside. Okay, now we have sine 3x. Sine 3x become negative cos 3x over 3. Okay, let me write all the necessary solution. X squared sine 3x dx is equal let's just multiply x sine 3x divided by 9, and then multiply become plus, right? Yeah, to cos 3x plus cos. Okay, so this is the answer. Okay. This. So let me write. Uh, can we simplify this method? Do you know why? Have you seen the pattern here? Okay. Let me give you what we are doing here. Okay. Uh, we have the u and p phi equal u phi minus integral phi d. Okay. Or let me use the board so you can see. So if you have the integrations, if you have seen these expressions, okay, and it's perfectly what we did, right? But eventually, when you have another CDU, right, you need to integration by parts one more time, right? So let's say if you are using the u is v and du is dv. So this is saying that we need to get the u dv and u is v. Okay. So what we did is we are making another uv, right? So uv. Wait, now I'm confused. uv uv minus the integrations of v du. And it's appear again, right? And you did the same thing, it appear again. And when it will be stopping, when you need to stop. Okay? If you see here, okay, you see x squared, right? And it's become 2x, right? And then 2x become 2, right? And later it's gone. It's 0. When you get the sine track, okay, we can integrate this directly and we get the last part, right? Because x squared, 2x, 2, and then 0. So what we need to do is maybe we can rearrange the pattern. Okay, you have functions that easily to be derived and functions easy to integrate based on these two. Okay, or let me use another simple function than this one. Let's use the wait. I think some of you know what I mean. So let's evaluate the integrations of x squared sine x dx. Okay. So let's say the x squared is easy to derive. Let's write d. This is to be integrated. Let's write integration, derivative integrations. Okay. Let's write the functions here and the integrations here. Okay. Okay, let's derive the x squared until 0. And then stop because we cannot do anymore, right? And integrate this, become this, and integrate one more time until it appears the cos x. Okay. And then remember, we have positive, negative, and then positive, negative, right? You will have the pattern, the positive, negative part. Okay. What we did here is actually rearrange the pattern in the integration by parts. Okay. So positive, negative, positive, negative. And what you need to do from here is multiply this to here. It's become your UV, right? Multiply this, and this. Multiply by positive, multiply by x squared minus cos x. So that will be our first part. And then multiply negative 2x, negative sin x, plus 2x sin x. And then plus 2 cos x. And plus c at the very end. And that's the integration. Okay. Some say that, oh, what is this method? You can argue, you can make argument. This is actually what we did in the integration by parts. But we rearrange which part that can be derived, which part that you can integrate it. Okay. And then positive, negative from here, positive, negative. And then you have positive, negative, positive, negative. Okay. I also did this in my high school, but at that time I don't understand why this is like this. I just, okay, I can integrate easily. But now I also know after I learning calculus, oh, this is actually this came from the very principle in the integration by parts. Okay. So if you doing this in exam, for me that's okay. But I don't know other professors, okay? Because I know that this is actually integration by parts. But do not forget the concept, okay? Sometimes you need to rearrange this sometimes, okay? In some cases. But most of the time, you can do this. Some professor call this method is DI method. But it's actually integration by parts. It's actually integration by parts, okay? Okay, another interesting point, what if, okay? Because it's easy to see it's 0 right here. From x squared, you get 0. What happens if it's not 0? We can still use it. We can still use it. Let me check. Okay. I think I got the other functions. Okay. Have you got similar like this before? No? No? You got this before? No? I think most students in Singapore use this. Or maybe, yeah, I think Singapore. I got this from Singapore colleague. Anyone got this before? Got? But you didn't know from here, right? Okay. So, but if you are maybe going to a different class and use this method, and maybe the professor asks, how did you do that? And maybe the professor said, oh, this is wrong. You need to be able to make an argument that this is come from this. Okay. Okay, let me give you another example. The case that it won't be 0. Okay, so let me try this. Okay, e to the negative x and then cosine x. Okay. My suggestions, because I think it's not too complicated, you can just use the UGV, integration by part method. I think it will be not too long. It's also fine. But if you want to keep a DI method, it's also can be done. But you need to stop before you're getting cycles. Okay? Because e to the negative x, you will get e, right? Okay. So let's write maybe this d and e. Okay. Derive become negative e x, and then derive once more. Got this. Let me stop here first. And then integrate become sine, and then integrate once more become negative cos. If I derive and integrate, I will be back to sine and e to the negative x, right? Um, then stop here first. Okay. And this is what you need to do. Um, so first we get this one, e to the negative x sine x, and then we get negative e, negative x, negative cos x. The last part is this part. Notice that this part, e to the negative x, negative cos x, is actually similar to our original questions. It's the same thing that we did before. So we rearrange and then divide, right? So we can write this as e to the negative x sine x. And then plus negative. And then negative integration. So the last part here becomes this. Okay, and then this part you can move to the left hand. Let me write this. So let me write e to the negative x 2. And then plus c. So you still use the DI method. So basically, most of the time, it will work for most of the functions. Okay, but it depends. Okay, it depends. So you have substitution method. You have integration by parts. Sometimes you work substitutions. Some maybe faster, but maybe the integration by parts faster. So you can also choose which method if you can do with all methods. But if you cannot substitute, then go to integration by parts. Or if you have like complex trigonometric functions, maybe you need to look for identity in trigonometry. Okay. Okay, I give you maybe one more last example, and then I think we can move to another part. Okay, let me give you the integrations of tangent inverse x dx. Okay, now I think if you just use the just the original method, uh, um, dv is dx, so v is x. So I think you can still get these same results. Well, let's just compare. This is later. And let me use di. So tangent inverse x, and then dx. And it's become x. And we cannot do anything up until here. Let's just stop here. And we get, I think, the same thing, right? We get the x tangent inverse x minus, and we need to use the substitution method from here, from this one. So we substitute the u is 1 plus x squared, and then du is 2x dx. So you get the half 1 over u du, and it will be half ln 1 plus x squared. So the complete solutions will be x tangent inverse x minus half ln 1 plus x squared plus c. So again, what I want to show you is if you have di, you have u dv. This is what you are actually, it's become du, it's become v, right? The same, right? The same principle. uv minus v du integration. Okay. It's going back to our original definitions in integration by parts. Okay. Actually, this method is just to rearrange the work so that you can work faster. But sometimes you need to go back to the basic one to understand what maybe um, there are some analytical functions that you need to analyze. Then maybe you need to go back to the original one. But if this is only the techniques to integrate, the faster you want, I think I believe it's a little bit faster. Okay. Okay. Any questions? Any questions? Kenapa juga? Okay. So again, the DI method. I'm not sure who invented at the very beginning, but it became popularized in, I think, in Singapore, and then maybe some in the United States. Yeah, I got it from my high school teacher, but he didn't explain why I get this crazy method. Okay. I give you some notes for special integrals. Okay, if I'm integrating the secant squared dx, this is easily tangent, right? Tangent. One of the most difficult integral in the elementary function integral, okay, is this. This is one of the most difficult one. Difficult, but you still can get the results from your knowledge. Okay. There are other you need to maybe use some approximations and other functions. But here it's still elementary functions. Okay. So example for non-elementary. Okay, for non-elementary, you have e to the negative x squared dx. You cannot integrate this, no, but you can approximate. Okay. And another one is sine x over x dx. Also, you cannot integrate this. Okay, and other functions. So this is called the non-elementary. Non-elementary functions. Okay. So non-elementary functions means, so elementary means any functions in terms of specific or let's say the simple functions that you have learned, like linear, polynomial, trigonometric, exponential, all of that we call the elementary. So you have specific uh, terms and specific visualizations. Okay, but for non-elementary, what you can do is first you can approximate some of the functions. You can approximate next semester in calculus 2 with Taylor series and so on. Some are you need to learn high level math, especially if you are. But I'm not sure will you learn that advanced level math or not. Maybe in the engineering of mathematics, some of the function will be applicable, but I'm not sure. But for our calculus, okay, we call this non-elementary. Non-elementary means when you integrate, uh, there are no sufficient method, regular method in integration by parts, substitution. You cannot do all the methods in this type of integrations. And that's non-elementary. But secant, you still can do something. Okay. There are several ways, but I think I just show you just one way that I think easy enough to understand. So secant, it's quite tricky actually. So let me write secant x. And then let's multiply the secant with the okay. So let's multiply secant x with the secant x plus tangent x. Secant x plus tangent x. Okay. Why? Do you know why? Because in secant, let me write here. If you have secant x, what will it be? Secant x tangent x, right? And when you have this, is of course it will go back to the secant squared x, right? Okay. When I multiply these two, the part at the top, it becomes secant squared x and secant x tangent x. Okay. So it becomes the secant squared x plus secant x tangent x over secant x plus tangent x. And let me write dx here. Forget to write dx. Okay. Can you solve this now? Okay, see the bottom part here, secant x plus tangent x. Imagine you derive this. Secant become secant x, tangent x. Tangent become cosine square x. The same. So you can use substitution, right? Right? Okay. So you can use substitution. So that is the first the method to integrate. So it's actually 1 over u, and this will become ln of secant x plus tangent x plus c. Okay. And I think this is quite helpful. Okay. But if you forget, you need to go to here, secant plus tangent, and going here. So by doing the secant x, if you were asked to find, let's say, secant, or maybe secant 5x dx, or maybe 4, you can do set of combinations. You can have secant x, secant squared x, and then secant x. If you want to integrate that, you can use this solutions. And secant 4x, you can secant squared and then squared, okay? And it's or maybe secant squared, and then secant 5, maybe secant squared and then secant cubed to do the integration by part. You can try maybe if you have some time to try. Maybe if I have time until maybe next Thursday or next Tuesday, I will do some of the secant variations. Okay, that is the integrations by part. So to make the class or the course keep on going, and I think I will give you the tools. Like for now, it's integration by parts. The next one will be the trigonometric, and then the partial fractions, and then after that we can have more exercises. Like Because some practice you need to combine. Some need to combine. Okay, so let's move to the next section, the trigonometric integrals. Maybe only a little bit, and then we can continue next Thursday. So um, let's start with the first variations. You will have sine cos variations. Okay, this means the sine x power m. Okay, and this is the cos x power of n. Okay, so let me give you the example, and then we can see the conclusion later. Okay. In trigonometric integrals, in sine cos problem, you need to remember just this basic trigonometry identity. So you can choose cosine or sine, and then change uh, to the equations. So you need to use this one, and then later you can use the substitution method. Okay. But first, if you see this sine, and then you have power of 5, cosine, power of 2, right? What you can do at the first time, you can split this sine 5. You can split that. And in this case, my suggestion is reserve one sine. Okay, here. Uh, so sine 4 and make sine x. Okay, I can split uh, become sine 4 cos squared and sine x. Okay, and this sine 4 is actually sine squared and then squared, right? So let me write this 4 as the squared, but squared here. Okay, and this sine squared is, I can write as 1 minus cos squared. Okay, and this become cos squared x. This is sine x dx. So why I need to change the sine squared to 1 minus cos sine squared? Because if you derive, cosine becomes sine, right? And with the substitutions, you can cancel the sign here. Okay. Then we can use the substitution method. So it will be minus 1 and then u squared and then du. Then you need to expand this form. So u squared minus 2u4 plus u6. And then we can calculate. This become 1 negative 1 over 3 cos 3x minus 2 plus 5 cosine 5x minus 1 over 7 cos 7x plus c. Okay, so this is for sine with power of 5, cosine with power of 2. Let's switch the 5 to and 2. Okay. So if you have sine squared x cosine with power of 5 dx, okay. We did same thing, but now it's cosine. Okay. Okay. We did the same thing, and then we need to change to 1 minus sine squared x. Okay. And then we let the u is sine x. And then we can cancel the cos x. And then the rest should be similar process. Similar answer, but different. And because it's sine squared cos phi. Okay, I'm giving you the summary, the conclusions. Okay, the conclusions. So sine m and then cos n dx. If cosine is odd, meaning the n is 2k plus 1. So this will be and then this should be 1 minus sine squared. So you need to make u as sine. Okay. If sine is odd, then let me write the 1 minus cos squared x, okay, cos and x sine x dx. And then u will be the cosine x. Okay. I think that's it for today. Okay. So if you see any variations in sine with some power and cos with some power, if it is odd and even, then you need to look the odd one. Okay. If the cos is odd, then you need to make the functions and making the u is sine x. Okay. And if you see the odd is the sine, then you need to make the u as the cos x. Okay. So the idea is actually you need to rearrange. Okay. Rearrange the sine and cos. Okay. Based on identity from trigonometry, and then split the functions. Okay. Split the function. And at least, okay, if cos is odd, you need to reserve one cosine. Okay, this one cosine will be cancelled by the sine. Okay, and if your sine is odd, you need to reserve one sine. Okay, one sine here. Okay, I think I will finish until here, and we will see you again at the Thursday class.